Why binary? Let's start. Every computing device you own, from the watch on your wrist to the server farm across the ocean, operates on binary. Ones and zeros. This is not an accident of history. It's because early engineers found binary convenient. It's because binary is the answer to a specific physical question. How do you store and transmit information reliably in a world full of noise? I'm going to tell you what noise is. I'm going to tell you and explain everything. So start with a coin. I wrote a little C program here. When you flip it, you resolve one bit of uncertainty. 1-bit binary digit, 0 or 1, 0 or 1, heads or tails. The word is not arbitrary. If you have n, the number n, equally likely outcomes, the number of bits needed to distinguish between them is log base 2 of n. For the coin, how many sides does a coin have? 2, so it's log base 2 of 2. For a die with 6 sides, it's log base 2 of 6, approximately 2.585. So you can't transmit a die roll in fewer than 3 bits if you need perfect reconstruction. But you can do it in 2.585 bits on average if you allow clever encoding across multiple rolls. This is called information theory, and it's the foundation of everything that follows. Let's talk Claude Shannon, 1948, the entropy of the random variable x. Here we go. H of x equals negative the sum over all x of p of x times log base 2 of p of x. So my parents were born before 1948. My parents being born before 1948, does that mean they were born before the creation of binary? No, it means they were born before the formal creation of information theory by Claude Shannon. But binary numbers themselves are much older. Around the 1600s, it was described in 1703 by Leibniz. He showed us that any number can be written using zeros and ones. Decimal is 1, 2, 3, 4. Binary is 1, 1, 0, 1, 1, 1, 0, 0. And he even connected binary to the ancient Chinese text, which uses patterns of broken and unbroken lines that resemble binary. Then you have binary logic and circuits from the 1800s. Mathematician George Boole invented Boolean algebra. This is way before 1948. Mathematics using true and false values. And then later, engineers realized that true can equal 1, false can equal 0, and this allowed electrical circuits to perform logical operations. And then binary computers, still before 1948, they already used binary. The Z3 in 1941, the Colossus in 1943. These machines used binary switching circuits. But what happened in 1948 is that Claude Shannon published a mathematical theory of communication, and he proved something deeper. That binary is not just convenient, it is the optimal way for transmitting information reliably in noisy systems. This is when the concept of a bit and entropy became formal mathematics. So 1703, binary numbers, 1800, Boolean logic, 1930s to 40s, binary computers, 1948, information theory. So the big idea is that information theory treats information as something measurable, just like distance or energy. It answers the questions like, how much information is in a message? What's the best possible compression of data? How much noise can the communication channel tolerate? What's the maximum data rate you can send without errors? Shannon looked at this abstractly, independent of actual terminology. He came up with the bit, he came up with entropy, which is this is his formula. Entropy is equal to the average number of bits needed to describe an outcome. So why does binary appear everywhere? Physical systems are noisy. It's far easier to distinguish off, on, 0 or 1, low or high voltage than many intermediary states. Binary maximizes the reliability under noise, and it underlies huge parts of modern technology. Internet communications, MP3, JPEG, zip, CDs, QR codes, cryptography, machine learning, LLMs, AI training. So if I had to say what information theory is in one sentence, it's the mathematics of uncertainty and the limits of communication. Or even simpler, how many bits are needed to describe the world? Entropy is the expected number of bits needed to encode an outcome, not the maximum, the expected. When the outcomes are equally likely, this is reduced to log base 2 of n. When they're not, you can do better. English text has an entropy of around 1.0 to 1.5 bits per character, depending on the model, but we store it in an 8-bit bytes. The gap is redundancy, and compression algorithms exploit that. So information theory tells us that binary is sufficient. Any information can be encoded in bits, but sufficiency is not the reason we use binary. We use binary because it's reliable. If you look at this voltage, it has two horizontal bands, high and low, noisy signal wiggling between them. Physical systems store information by distinguishing states: high voltage, low voltage, magnetic orientation this way or that way, a pit or a land on optical media. The problem is noise, thermal vibration, electromagnetic interference, manufacturing variation. The signal you send is not the signal that you receive. With two states, you can define a threshold. Above the threshold, interpreted as 1, below as 0. The noise margin is the distance from the nominal level to the threshold. As long as the noise does not push the signal across the threshold, the bit is recovered correctly. There was ternary for some time. There was a ternary computer, the Saturn, 1958, Soviet Union. It used -1, 0, and 1. It was more efficient in some theoretical measures, but it didn't persist because the physical advantages of binary, sharp thresholds, straightforward implementation with switches that are either on or off, those outweigh the theoretical density gains of ternary. And today, modern binary logic uses transistors as voltage-controlled switches. There's physical, larger transistors that you can put in your everyday modern electronic product, but then your processor in your computer has many, many, many transistors, billions of transistors. A CMOS inverter, one transistor pulls high, one pulls low. The output is driven strongly to one rail or the other. There is no stable intermediate state. The circuit has positive feedback near the threshold, snapping the output to a valid level. This restores a degraded signal to full amplitude. This regeneration is harder with multiple levels. So the answer is 2 symbols are sufficient to encode anything. Physics, 2 states are the most distinguishable given real noise. Binary is not a compromise. It is the optimal solution to a constrained optimization problem.